burning through everything. It just focus on the local neighborhood. So it is basically what is neighborhood attention is. So you look at this picture, on top we have the regular attention, would go through every voxel, and then on the bottom you only have a kernel which would only concern with like the local information. So the trade-off is we have a huge boost in local accuracy, but then it comes with it's like if your local neighborhood has an error, so it's more effective. So there's a local bias that comes with it. There's same thing with CNN. So every time you use a local kernel, you get the speed up, but like there's also more bias.
Could you go back to the earlier slide? I just have a quick question. So this seems like the query key and value are linear. But in the second figure, you were showing that those are matrices, like 3D volumes.
And it is?
No, like in figure 2, if you look at the query and the key size, the value size, key and value size. No, like if you go back to that figure, the second one.
This one.
Yeah, the query size is not the same as the key and the value in this figure.
Okay, yeah. Well, the key and values often have the same size, but the query doesn't have to be. It only have for the dot matrix. It only have to have like one course. Or but you can do to produce the context matrix.
Okay. Okay, I think you got cut off. Somehow the internet was a bit sketchy. But yeah.
Absolutely. So yeah, well, I was the query is and the key values.
Being your voice is broken.
Yeah, I think he got disconnected somehow.
Yeah, the connection was bad.
Yeah.
Connection issues in the conference room, so I'm on my phone right now. I'm trying to log back in my laptop. Can you guys hear me?
Yeah. Are you using the Wi-Fi, or because your phone connection seems to also have a network issue?
Hey, can you guys hear me? Can you guys hear me?
Yep.
They echo to each other.
Yeah, because sorry, I having connection issues in the.
Oh, wow.
Yeah.
Yeah, maybe you should turn off your video. That might help.
Okay. Yes. Did you hear the explanation or not Abra,
Yeah.
did I did the go through? Okay.
Yeah, I see your screen now.
Oh, yeah. Values either size, but the query doesn't have to be share one. So for
Voice
example, the
is
query is
still
2x4.
choppy, very choppy.
Okay. I'm in the conference room right next to the office. I choppy. Now.
Yeah, it looks like you may want to either change your location. I'm not sure if you're on Wi-Fi. Otherwise, you can. If there's LAN, you can use the LAN from the conference room. Yeah, it's very slow.
Yeah. Yeah, I keep disconnecting. Can you guys hear me?
Yeah.
Yeah, sorry. Well, I don't know why internet's not working in this location.
No, it could be the rain in some ways. But now we can hear you clear, I think.
Okay, so I'm just gonna move on. So yeah, for this one, the query and keys values can be different as long as they share one dimension. So if the query is 2x4 and the key is 4x4, you can still do the dot product to get the context matrix. So yeah, that's the answer to April's question. And then so for the next one, so we're gonna use the attention network to fit IVIM, and the next step is to generate the ground truth. And they do this by using the palette noise map. So basically, the palette noise is, you can think of it as like a mathematical formula. When you pass in the appropriate parameter, it will generate a fractal noise map that is normalized. So all the values between this fractal noise map, as indicate like by A, is between 0 and 1. So once you have this fractal noise map, you can do a threshold setting to generate artificial tissue type. So anything between 0 and 0.2 and 0.5 is gray matter. Between 0.5 and 0.8 are white matter, and then the rest are CSF. And once you have this tissue type map, you can use a dictionary to input the appropriate D star, F, and D values to fill these tissue type masks according to literature. And then you can fill them two ways. First, you can sample them uniformly, and then the other way you can do it is sampling them using a Gaussian distribution, which is more realistic. So you have a very diverse set of ground truth using this palette noise approach. The other way that the author used to generate their tissue type is that they're using a random neighbor algorithm. So you start with the central voxel, and this central voxel can be the D star and F you got from literature, and then you're gonna fill up the neighbors with copy of the central voxel. So if you look at B, if neighbor is 0, then all the neighbors gonna be different from the central voxel. If the neighbor is 1, you have 1 copy, and the neighbor 2, you have 2 copy, and so on and so forth. And it goes all the way up to 8, so like all 9 voxels are the same. So this is a way for them to control how uniform these tissue batches are, and how they can affect network performance later. And this is also how I use to generate our synthetic data sets. So once we have all the ground truth, we're gonna test them using 3 candidate models, the CNN, the cell attention neural network, and then the neighborhood attention networks. And here's the testing result. We have 2 modes, the unsupervised learning mode and then the supervised learning mode. The unsupervised learning mode is in orange, and then the supervised learning mode is in brown. So for unsupervised learning, once again, we have the superior parameter mean square error values, and then the attention neighborhood network is the best one. And you can see a clear distinction between the normal DNN, which is in green, the CNN, which is in blue, and then the attention network, which is in like orange here. So superior parameter fitting. And then for supervised learning, then you have the superior signal MSE compared to the unsupervised learning method. However, these three methods have roughly the same performance, mostly because the noise. So if you don't see the IVIM ground truth and you have to fix the neural network using the measured signal, if the measured signal is noisy, you cannot take advantage of the spatial information. So that's why all these different architecture having roughly the same performance. So that's the takeaway. And then here we're gonna look at the unsupervised parameter construction performance in more detail. So we'll start with an overall result, which is comparing convolution neural network and transformer network. You see that the green line here is the DNN baseline. So both the CNN and the transformer network performs way better than the conventional deep neural net due to the spatial information. And here, through 0 to 8, you see how this network performs with different variation of spatial configurations. So if there's no correlation within the neighbor, so neighbor 0, then obviously the performance is going to be the same as DNN. However, if the neighbors are correlate higher and higher, so the higher correlation between the neighbors, the better the neighborhood attention network NNCNN perform. So this is interesting. Performance has to do with the uniformity of the tissue type we're looking at. So if you're looking at purely white or purely gray matter tissue, and the CNN and attention network kind of perform better than DNN significantly. So that's the takeaway. And then the last thing we're gonna look at in terms of performance is the spread. So the error spread. So up here you see the conventional method least square and then least square neighborhood. So for least square, especially for D star, which is right here, you see that there's a lot of spread. However, if you take the neighborhood approach, which is fitting least square not only for one voxel but like for a neighborhood of like 3x3 or 5x5, it somewhat reduce this error spread. And once again, you can see the same thing happening in the supervised learning. So for voxel-wise, which is the DNN convolution network and the transformer, if you look at this last column, which is on the diffusion parameter, you see that the spread starts to 10 for supervised learning. However, this doesn't really have an effect on self-supervised learning. Because once again, because of the noise and the lack of ground truth. So this is the second investigation of this paper. We have determined that spatial prior helped in the last investigation. Now we're gonna see how much better we can improve our network if we include more spatial information. So here we have the ground truth on top, and then the least square performance here. And what we're gonna focus our attention on is the error map. Right? For the error map, you want it as dark as possible so there's no error. So ideally, you will see all blue, like the one on the left column here. So for the least square method, you see that there's some error in the F reconstruction and a lot of error in the perfusion reconstruction. For the attention network and a deep network, for DNN, you see there's a lot of hallucination occurs at these stars. However, if you increase the voxel size from 1x1 to 3x3, you immediately see that the hallucination becomes less, and then it goes all the way to 17. When it reached the 17x17 neighborhood, which is a huge patch of our voxel, the hallucination stops. So the spatial prior has a regularization effect. So the more information you see, the more noise resilient it becomes, and then it fits the diffusion parameter better. And then once again, so we'll also look at the error spread in this context. So here you have the ground truth as the diagonal line, and then you have three tissue type. You have the white matter in what's the color? It's brown, and gray matter is in purple, and CSF in orange. And you see that the gray matter and CSF fits the ground truth pretty well for all fitting type. However, for least square, the white matter squared is all over the place. And so the most of the error is in the white matter, which is unfortunately have the most clinical application in CSPD. So for the attention neural network, once again we see that there's a large spread in white matter, and then this spread decreases as we increase the neighborhood size. So with larger receptive field, we are able to reduce the bias and have a very accurate perfusion measurement. So when it reaches to like 17 by 17, the D-star accuracy is fairly respectable, even for white matter. So last but not least, we're gonna look at this from another perspective. This is coming from the mean absolute percentile error. So going from left to right, you have 1 by 1, and then all the way to the right, you have 17 by 17. And you can see a very clear decrease in absolute percentile error as you increase the field of view of the neural network, or the kernel size of neural network. So the bigger the neighborhood, the better. But the trade-off is like 17 by 17 is huge, and it's gonna take forever to train. So if you have the extra computational resource, you can go for it.
Sorry, Ben.
Yes, sir.
So 17 by 17 really means you look at your neighborhood reaching that range?
Yes. So the 17. So it's a big square with your voxel of interest in the middle.
Is that realistic? I mean, if you're looking at a voxel of your image and then try to average all the 17 by 17 around it, and that's what.
Yeah, I would say it's not very realistic. That's a big size, and the training time gonna be like very long. They said it's 100 hours, 95 hours plus, but they just do this so they can prove a point that the kernel size matter. So you have a very big kernel, you can incorporate like a big chunk of information and then that improves your fitting. I don't know if that answers your question. But there's okay there. Then at the end, like right after this, toward the end, they don't do one for the in vivo data, and we'll see the benefits of this increased receptive field later.
That'd be good.
All right. So before we get into that, the next exploration that they did is that they will test the performance of how variation of the training data affect the testing result. So their hypothesis is that the more similar the training data to the testing set, the better the fit. And they define similarity in two different ways. So you have the spatial context. So you have this neighbor random, which is shown underneath here. So and you also have the structural random, which is generated by Pellet noise. And they have the ground truth is the Pellet noise generated. So they were testing whether if I use a neighbor random distribution and use it on a Pellet noise test set, will the performance decreases. And then similarly, they doing the same test with distribution. So they're testing if you have a Gaussian ground truth and you use uniform distribution training data set, will it matters. So the result is quite interesting. They measure it by percentile error, and so here you once again, just to remind you, the ground truth is the parent mask with Gaussian sampling, And then the bottom label here, you see on this combination, it's just different type of spatial and sampling combination. So random uniform means that if you go back, you have the random neighborhood spatial distribution with uniform sampling. That's all it means. And you can see here, the takeaway is fairly obvious, that the more similar training data size, data is to the test set, the better performance. But it turns out that spatial similarity doesn't really matter too much. So if you look at the top two, right, you're going from the random neighborhood to like the pairing spatial spread. It did increase the performance, but not by much. However, if you switch to the correct distribution sampling type, it has a dramatic effect. So the way you sampling the data matters way more than how the data structure, which is interesting. The other interesting point that they found is that, okay, the training data set similarity does help, but if you have a very big neighborhood, it doesn't really matter. So there is improvement, but it's not as dramatic. So the last but not least, they test their fitting methods onto in vivo data set, and this one is only have one healthy volunteer. It's the guy that wrote the paper, and then their ground truth is gonna be the 12 repetition least square fitting, and they're gonna compare the mean square error and the coefficient of variance to evaluate the performance of these fits. So since in vivo subjects, you don't really have a ground truth. So what they do is they fit least square 12 times and then average the data to get the best fitting method. So in a sense, this 12 rep least square fitting is gonna be our ground truth. And then they're gonna vary the tension network for different receptive field size. So you have 1 by 1, 3 by 3, 7 by 7, and then 17 by 17. And then they tested on different combination of spatial and then sampling training data. So you have random uniform and random Gaussian. So right away you see that in smaller kernel or smaller receptive field, the two distribution is quite different, and in fact the uniform sampling perform much worse than the Gaussian sampling. However, as the receptive field gets bigger, like toward the bottom, the difference become minimal. And by the time they reach 17 by 17, the information that they give is very similar to the information given by the 12 repetition least square. So there's definitely agreement between the best fitting neural network and in this case the quote unquote least square ground truth. And yeah, well, that's the takeaway. And then finally they look at coefficient variance, and for this is the measure of stability. So you want a smaller coefficient of variance as possible. And if you look at least square or D star, it is highly vary. So like the fitting between each repetition may be all over the place, and this is the reason why IVIM is not very popular in the clinical setting yet. But if you use the neural network, because of the spatial prior, the variance in D star is much smaller, and the smallest when you have the biggest. Actually, it's smallest when when the voxel size is smallest, because it doesn't have as much spatial variance. But even with the spatial variance, the trade-off is way better than using least square. And yeah, so in summary, we have seen IVM fitting using cell attention network hugely improve the error fitting and the spatial stability. But this improvement only benefited supervised learning, and for the reason that unsupervised learning has to rely on noisy voxel, so it cancels out the spatial prior benefits. And the performance scale with larger receptive field, so the bigger the kernel, the better our performance. And then similarity between training training and testing data does matter, but it is less critical when you have a big receptive field. And attention neural network in general was superior to CNN and DNN. And then the limitation of this work is that it has to be supervised attention neural network scheme. So if you do not have the ground truth, it is very difficult to apply this method. So that means that every time you want to bring this to a new protocol, first you have to fit the least square to get the ground truth, and then you use that least square ground truth to train the neural network, and then that kind of defeats the purpose, in my opinion. And then the 17 by 17 attention network takes 95 hours on with the A100. So it's a huge computational learning cost. So every time you train this, it's about $200. So yeah, this laid the basis of our neural network, which is like how to modify this attention network for supervised fitting, for save computational resources, and possibly have a more reliable fit. And that's all I have for today. Is any questions? All right.
So Ben, this limitation you mentioned at the end is huge, and hopefully your work inspired by this will try to overcome those two limitations.
Yes, that's the hope. Maybe even one is good enough, but yeah. So, but right now we tackle two because we kind of sidestep doing the self attention. We have a cross attention loss. We do not do the transformer network at all, because we do not have the computation resource for doing this full transformer. So we're structuring the attention formula as the loss function instead of the network. Yeah. So using bone brain tissue type. So yeah, this is we're using this as a scaling loss instead of like reconstructing the whole network. Oh yeah. Hopefully, we have the synthetic data works, and so there's some optimism there, but I still need to get more evidence.
Sounds good.
All right. Yeah, that all I have. Thank you all.
Thank you, Ben. It was a nice presentation.
All right. Yeah. All right. You guys have a good Wednesday.
All right.
All right. Take care.